Okay, so we studied RF inductors last class, right? So we looked at a few samples, we looked at the top view, side view, we looked at the inductor model, and I think in the last couple of minutes we went through a bunch of stuff, so let me cover that again a little bit more slowly. So then we look at transformers. So you'll be using transformers in certain cases. They are useful in differential circuits. So instead of having two inductors, in many cases it's more beneficial to have a single transformer. You might have cases where you want to convert from differential to single-ended. You use transformers in those cases. So they are useful. They are quite useful in many kinds of circuits. So we'll quickly look at transformers. So that is the basic idea is the same between inductors and transformers. The only difference is you want some symmetry in transformers between the primary and the secondary. We'll look at that. And then today we'll also cover capacitors and varactors, because just to complete out the passive circuits we'll be using for the tanks. We'll look at what kinds of capacitors are available, what's a varactor, what does it do, and how it operates. Okay, so we looked at last class. We looked at the compact model, right? Okay, so this is your substrate, and let's call this node A and node B, which are the two nodes of your inductor. And then we also had this coupling cap CC, Cox, RS, LS, the capacitance and resistance of your silicon. Okay, and so we also looked at the figures of merit. I think that's where I started going a little bit faster, because we only had a few minutes. So let's look at the figures of merit again. So the first figure of merit, most important figure of merit, is the Q of the inductor. And we know, right, the physical definition is 2 pi times the energy stored over the energy dissipated per cycle. So that is the physical definition. And we also saw that a more useful definition for us is to use the circuit level definition, which is the imaginary part over real part of the impedance. So let's say your inductor has the two ports A and B. So the way we are going to evaluate the Q is to look at Zn, which is also of course 1 over Yn, and we are going to use Q equals imaginary part of Zn over real part of Zn, and this also happens to be imaginary part of Yn over real part of Yn. Okay, all of these are equal. You can use either one of these. And obviously when you have such a complex model, your Q is going to be a function of a bunch of things. It's going to be a function of your LS, RS, your CC, and so on, all these parameters, because it depends on both the real and imaginary parts. Okay, now we also saw that for the inductor itself we could define it as obviously if you use this definition, it's not valid at all frequencies, because you're already assuming that the imaginary part is positive for an inductor. Okay, so let's say you have a series resistance R and inductance L. Omega L over R is the definition, but it's valid for an inductance. But at some frequency, so the effects of these capacitances is only going to increase with frequency, right? Because the impedance gets lower and lower. Imagine at very high frequencies, really high frequencies, CC is going to be a short. You don't have an inductance at all between A and B, right? So obviously, it's no longer an inductor after a certain frequency, and that is what we call the self-resonant frequency, and we're going to go to that next. But the other important thing to notice, if you use this definition, so for example, if you have some capacitance, right, we looked at it as omega L minus 1 over omega C over R, right, you'll get some expression like this. You have some inductance effects, some capacitive effects over the resistive effects. And this is valid only as far as the system is an inductor. Beyond that, the numerator will get negative. So when you plot it, you will see some negative Qs in your when you do your simulations. But you just have to keep this in mind. The Q is definition is no longer valid beyond that. Okay. Okay. Now the other thing we looked at is the self-resonant frequency. Right. This is the frequency beyond which the network between A and B is no longer an inductor. It's a capacitor effectively. It will still have its own resistive parasitics, but it's a capacitor effectively. Okay. So this is the frequency at which your self-inductance and all your self-capacitance resonate. Okay, there will be one frequency at which your capacitive effects and your inductive effects put together will resonate, and that is the self-resonance frequency or just self-resonance. And the thing you have to note is, as we saw, real inductors have capacitive parasitics, right? Have a lot of capacitive parasitics. If you look at it, you have the CC, you have COX, CSI, and so on. And if you actually look at real capacitors, we tend to think of capacitors as ideal capacitors, but in reality, they have some series resistance. Okay, they'll have some series inductance of the leads of the connections you make to your capacitor, and of course they have the capacitor. And you can draw a similar parallel for real capacitors. Real capacitors will have inductive and resistive parasitics, so they'll have their own self-resonance. Okay, so what you're doing here is also valid for capacitors also. And if you take more complex circuits, once you start building, let's say oscillators or LNAs or something like that, you'll start to make tank circuits out of these two, which gets more complex. So once you start adding all these effects in, you may end up seeing not just one resonance but multiple resonances, right? So it gets more difficult to analyze by hand, so you'll start drilling on the simulator, and that's why modeling is so important. Your model has to be very accurate to model all these effects. Okay, and if you look at your Q versus frequency, so we saw at very low frequencies the inductance dominates, so it will increase somewhat linearly. And then at some point of time the capacitor effect starts to dominate, and then if you just use the basic definition imaginary over real, you'll see it cross the 0 point at the self-resonant frequency. And we saw last time that you want to operate somewhere close to the peak, because this is you're interested in maximum Q, because that gets as close to the ideal situation as possible. Okay, so let me call this FRF, which is your desired RF frequency. Okay, so now let's go back to our model. So what can you do with your inductor to help increase your Q? Because you have control over a lot of parameters, right? We didn't go over this last time, but actually we went over it in brief. So we have control over width of the trace, right? We have control over spacing between adjacent traces. We try to design the inductor such that you get positive mutual effects and remove negative mutual effects. So you have a bunch of parameters you can play with. Okay, and each one affects the other one. If you try to increase your mutual effects, you might for the same inductance, you might end up using a larger area and therefore a larger capacitance substrate, which means a lower self-resonant frequency. Okay, so some very basic trade-offs you can do. So if you increase the width of the trace, for example, right? So if I go back to last week's lecture, so let's try to okay. So this is the width of the trace. What happens if you increase the width of the trace? What do you think is going to happen to, let's say, RS? RS will decrease, obviously, right? Because RS has two components. One is the DC resistance, which will be valid at all frequencies, and there is also a skin effect, right? So definitely the resistance of the inductance would decrease. So that you know. Now what do you think will happen to COX? It will increase, right? COX is going to increase because now you have a wider plate. So your COX is the capacitance between your metal line and your oxide, right, and the lower layers and the substrate. So that will increase. Okay. Now what do you think will happen to Cc? Probably nothing much, because it is the turn to turn capacitance. That's what you're trying to model. So nothing much may happen. It will change, but probably not. It depends on how much fringing you have and so on, right? Some higher order effects which are not very obvious to us. Okay. Similarly, if you increase your diameter, you're going to increase your CSI and Cox. Okay. And you probably have, it's not completely obvious what happens to RSI. You have a larger area, so you have a larger area over which you can have losses. So typically your RSI would go down and your inductive losses would go up. Okay. So all those things will work together to change this profile. Okay. So in some cases you could have the Q getting higher, but self-resonance getting lower, which you may be perfectly okay with. If this is the frequency which you want to operate at, you are really not worried too much about what happens after that, because you are interested in a very narrow band. Okay. So the reason I'm explaining all these things is because we are going to announce our first project. You're going to be using a software called Acetic, and I'm going to give you a certain area you can simulate with. Okay. A certain maximum area you can use. Okay. And I'm going to give you a certain desired frequency you want to target. And what I want you to do is, in that given area, I want you to, each one, it's going to be an individual project. So you can choose any kind of inductor topology you want, right? There are different kinds of inductors. If you want to do a little bit of we covered one or two in class. If you want to do some extra research and read some paper and come up with a newer structure which gives you better Q, perfectly fine with me. But I'm going to give you a given area. Okay, you need to maximize Q at a particular frequency. Okay, so you'll be choosing different architectures. You'll be varying the trace weight. You'll be varying the spacing and so on, right, in the software, and that will help you understand the trade-offs in inductor design. Yes.
Suppose you are designing a transmission line.
Okay.
For a given substrate with a given epsilon value.
Okay.
We'll have a particular track width for a given impedance. Suppose,
Yes.
So now in this case, suppose this has to be interfaced with a given transmission line.
Okay.
So that track width will be governed by the impedance that we want.
Yes, but in this case, remember that we are looking at we are not looking at transmission lines. We are actually looking at lumped element models. Okay, because these are not going to interface. They are going to interface with circuits rather than distributed systems. Okay, so the main reason. Okay, so earlier when people used to work with discrete components, right? The distances and other things were large enough such that they were comparable to the wavelength, right? Maybe several orders higher than the wavelength of the signals you work with. Whereas now we have reached a point where on an IC, the connection between, let's say, between a transistor and this inductor, right, or the next amplifier stage is so short, is much shorter than the wavelength of the signal you're working with. So that means you don't have to consider distributive effects. Okay, and at that point of time, you need to make a decision on whether you want to match the impedances or whether you want to work with lumped elements and go with. For example, I think we discussed this in the first class, which is inside the chip, right? You try not to match. Let's say if you have an LNA, you want to drive a different circuit. You don't necessarily have to match the output to 50 ohms. Outside the chip, you want to match to 50 ohms because you have come to the domain where microwave effects are very predominant. Inside the chip, your distances are much shorter. Okay, so you try not to. You have to burn a lot of power to actually drive 50 ohms. So you want to try to avoid it if possible. Okay, so that's why we tend to. You will find a few cases where the cases where you would end up matching to 50 ohms are in case of impedance matching, right? But there we are already assuming lumped element matching, right? You are already assuming you're using lumped elements and to interface with distributed elements. You know, a lumped L and a lumped C of certain values will transform the impedances from 50 ohms to 200 ohms, right? So there is no problem in using lumped element models. Okay. Now what else can you do? So we looked at the trace width, trace length. Okay. So what else can you think of? Okay. So if you go back to your model. Now one other thing you should know, if you look at processors, right, CMOS processors, you have multiple metal layers. Nowadays you have maybe 5, 6, 7 layers, right? And if you look at the types of layers, so the lowest few layers will be quite thin, okay? They are meant to interface with transistors, capacitors, resistors and so on. They'll be quite thin, very resistive. They have a much larger capacitance to the substrate. The higher metal layers are usually thicker, and quite often they are thicker because you want them to be thicker, because you tend to use them for specific cases like RF circuit design, where you want them to be farther from the substrate and you want them to be thicker, because the farther you are from the substrate, your Cox reduces, right, and your RSI will also reduce, because your eddy current losses through the substrate will be much lower, okay? So you want them to be farther higher metal. So in general, you would want to, when you want to design your inductor, you want to use a higher metal layer, okay? Typically the highest metal layer you have access to would be the one you would start off with, okay? Then you might end up using the next metal layer. We saw last week there are cases when you want to connect to both the ports, you will always need an underpass, so you may use the next layer for an underpass, okay? Or you might, if the next layer is also a thick layer, it has high resistivity, you may use a combination of both the layers, right, to create a very good, very high Q inductor. But you'll be trading off the underpass, you'll be using an even lower metal layer, so that underpass may dominate your series resistance, for example, okay? So there are lots of trade-offs depending on the type of inductor you choose to design. Yes. It will, because that as long as there is signal current flowing through a particular metal layer, that metal layer is at a particular distance from your substrate, and that is going to decide the value of the eddy current which is flowing through the substrate, right? So if you keep using so let's say if you had an option to use the topmost metal layer, okay, what would happen is you'd be a little bit farther from the substrate, so your RSI would be lower than if you create an inductor just on the adjacent metal layer. So let's say you have 6 metal layers, right? So let's call them M1, the lowest one, to M6, right? So if you create the inductor only on M6, that is the best you can do, right? Okay, so now let's say you create it only on M5, that is definitely going to be worse, because RSI is going to be higher, because it's closer to the substrate, so your eddy losses are going to be higher. Now, however, remember there is a trade-off. Suppose your M5 is also a thick metal layer and has low resistivity, you can actually put M5 and M6 in parallel, okay, and create a what looks like a much better inductor. So what you'll be doing is reducing RS, but you'll be trading off, because now you have signal current flowing through M5, so your RSI will increase. It depends on which is dominating, okay? Exactly, it is not necessary that either Q, you can't say without analyzing what the distances are, without really running the electromagnetic tool, okay? It is not that intuitive. It depends on the actual distances from the substrate as well as the actual resistivities of your metal lines. Is that clear? Okay, we are going to come to that next. Okay, I think I quickly mentioned that last week, but that is the next thing we are going to look at is what is called a ground shield. Okay, now if you see, the losses happen through RSI because of magnetic fields causing eddy currents to flow through the low resistivity substrate. So what can you do? If you actually have a metal line, let's say a metal plate between the inductor and the substrate, right? That metal, and you ground that metal line, metal plate, that is going to shield your magnetic substrate from all magnetic fields, right? And because it's a perfect conductor, there are not going to be any, it actually gives a return path for the magnetic field, but there are no eddy current losses, because you're assuming it's very, very low resistivity, right? Okay, so now if you do that, what do you think will happen? So let's say we have actually that's okay, yeah. So you have an inductor, okay? Now what we're going to do is we're going to put a ground shield, okay? Now you will still have some eddy current flowing through the ground shield, but because of the low resistivity, I square R losses will be lower, okay? So let's assume that is the case for now. Next we'll look at what happens if that is not the case. Now what happens, so let's say this was on M6, okay? Which layer would you use for the ground shield? Anybody? M? So you want to use M5, let's say. Okay. So what is the difference between using M5 and M4? Right? Cox is going to get lower if you use M4. So obviously you actually, in the end, you don't want to use, you want to use M1, right? That's the farthest. So your self-resonant frequency of your inductor will be higher. Okay? Okay. So let's say you use M1. Okay? Can you do even better? What is the? Okay. So you can actually use your poly layer, right? So let's say you can even use your poly layer. Poly layer has a slightly higher resistivity, but you can use your poly layer. So that is another conductive semi-conductive layer between your inductor metal layers and your substrate. So you can use your poly. So that is another option. Yes, but because they are closer, you may actually end up having a curve which looks like this, right? What is it? What is the use if you have something like this? Resonant frequency. So remember, if your Cox keeps increasing, your M5 is actually fairly close to your M6. So your actually what I've drawn is obviously exaggerated, but so let's say your Q actually gets much better, right? So let's say, but so it goes something like this, let's say. So now it's no longer usable, right? Now it's no longer usable. You don't want that. So you may want to use M1 or poly. Okay. So now you can do even, turns out you can do even better, because let's say this is your ground shield. So ground shield will still have some eddy currents, right? What you can do is, you can actually do, so let's, I'll tell you what this is for, but so what you can do is you can do what is called slotting. Okay. Okay, so each one of these is actually a metal or poly strip, okay, and each one of these lines is a slot. So it's basically an empty space between adjacent metal strips, right? What will happen? Obviously there cannot be any eddy current flow, because now you have slotted it, you have created an open circuit. Is that clear to everyone? So eddy current tends to flow in a particular direction, circular, and now you have completely stopped the flow of that. And you want to ground all of these strips because that gives the best shield. So you would typically put to connect all the conductors together, you would put, let's say, a central line, a diagonal line to ground them effectively. Yes? Okay. Okay. So you have an inductor on M6, okay. So now you want to put a shield. So you have an option. So this is a substrate is so low, okay. So now you have option of M1, M2, M3, M4, and so on. So the way these processes work is you actually have the any area outside metal is covered with oxide, okay. So the heights of the metals with respect to substrate are constant, okay. So if you have M1, it is always at a certain height from the substrate, and between M1 and substrate you have oxide. If you have M6, it's much higher than the substrate, and if you don't put any metal lines below it, there is just going to be oxide, right? So the Cox, remember, the self-resonant frequency is decided by your Cox and your CSI, and CC is usually a much smaller effect, okay, because it will usually be in femtofarads, whereas Cox and CSI could be in several tens or hundreds of femtofarads, okay. So what happens is, as you keep using closer and closer metal lines, if you use M5 for example, you have oxide between M5 and M6. Obviously the capacitance Cox depends on the thickness of the oxide between M5 and M6. So if you use a closer metal layer, you will have a higher capacitance, right? So you want to use a farther metal layer. Yes? Actually, you are actually going to ground this metal shield. At the bottom. No, you would actually want to ground, if you want a good shield, you have to ground it very well, okay, which means even if you use M5, you have to ground that M5 very well, which means any metal layer below it, you don't care what happens to it. What if I have ordered it? Okay. Okay, so you want to create your inductor, you want to use M6 to M2 and ground M1. You could do that, but remember, so if you do that, right, the CC will first of all increase because your inductance is, you have parallel, combinations of M6 inductor, M5 inductor, and so on. So that will increase, and of course your Cox will also increase because that is at the end of the day, the capacitance to substrate will go through M1 to your substrate, right? So it will still be high.
So if we use a lower metal layer, like we can CSI increase because the metal layer is getting closer to the substrate, so that capacitance is not increasing.
So the metal layer to the substrate capacitance is actually Cox. Okay, CSI is actually, it's to model. So remember that it's a semiconductor, right? It has a certain ability to hold charge. It's a bulk substrate, and it has a certain ability to hold a certain amount of charge. So that you are representing it as a lumped capacitance. Okay, so CSI itself will be more a function of your doping levels and so on. It will be a function obviously of your size of your inductor, because the larger you go, you are interested in the amount of substrate below your inductor. Is that clear? Okay, so that is the reason why you want to use the lowest metal possible. Some people prefer to use poly, which has a slightly higher resistivity. In your simulator, you can try using either one and see if it helps you. And quite often you will see that adding the shield actually helps a lot with Q. Okay, depending on the substrate resistivity, you can actually get anywhere from 10 to 30% increases in Q. Okay. Now the next thing we looked at was there are still going to be some eddy currents which flow through the shield. To prevent that, those eddy currents, we are going to do what is called slotting. So you have bunch of metal strips which prevent circular current from, yes. Because, okay, so what are the losses in the inductor? The actual power losses in the inductor come from two sources, right? One is series resistance, other is substrate losses. Those are the only two losses. Okay, how do you improve the series resistance? Make the trace wider. Okay, use a metal layer with lower resistivity, which is usually the upper thicker metal layers. Or if you have options, there might be extra process options which may allow you to use some special copper metal layers. Copper usually has a slightly lower resistivity than aluminum. Okay, so you might want to go in for that if you can spare the expense. Okay, so that is how you decrease RS. Okay, next step is to reduce RSI. RSI basically models the eddy current losses. Okay, so you have time varying current flowing through your inductor. Faraday's law, you have eddy currents flowing through the substrate, and substrate heats up, right? So you have losses, and obviously the farther away you go and you shield it from substrate and so on. Is that clear? Okay, and of course you can do slotting, and that will improve your Q even further. Okay, now what else can you do from a process point of view? If you can spare the expense, you can go in for what is called a silicon on insulator process. So SOI processes, instead of having low resistivity process, you have a high resistivity layer between your substrate and your devices. Okay, which means effectively, so that may be like let's say several microns or maybe 10 or 20 microns thick, and that will form a high resistivity layer between your substrate and your inductor, which means your eddy, there will be very little eddy current flowing through the high resistivity layer. Okay, and you have effectively pushed your substrate even further. Okay, if you look at Qs of a standard digital process, right, if you just take no extra options, no thick metal layer, nothing, you will have Qs between 5 and 10. Okay, if you go for thick metal layers, you can get maybe 15, maybe 20, and if you go for SOI processes plus all of these, you may get 25, 30, sometimes even higher. Okay, so it all depends on what you choose to do with the process, and of course your topology matters. So each case may have one ideal type of inductor you want to use, because the actual Q depends on so many other factors the way you design the inductor. Okay. Okay. Then what did we do? We looked at of course the last figure of merit was the area, right? You can only afford, it comes down to cost, you can only afford to use certain amount of area for your inductor. Okay. Okay. Now let's look at transformers. Okay. So we know we want to use them in differential circuits, right? Or maybe to do differential to singulated conversion. And what do you know? If you are using them in differential circuits, what other condition do you need? Symmetry, right? Very important, differential circuits. Okay. So let's say you are going to design, what else do you need? You want your mutual inductance to be as high as possible. In other words, your coupling factor, right? Coupling factor is usually K. You want to increase it as much as possible. Okay. And there may be certain cases where you might be interested in a specific K. Okay. There may be certain cases where for proper operation of a circuit, you wanted to have, let's say, K equals 0.8, coupling factor of 0.8. Okay. Okay, so let's look at some transformer structures. So let me go to this and let me choose this layer. Okay, and I'm going to use a slightly, let me see which color I can choose. Okay, so let me choose this. So that is your underpass. Okay, so let's call that P1 and P2. Those are the two nodes of your primary. So let's say you want a completely symmetric winding, right? So let's go back and let's go back to this layer. Okay, I'm in a little bit of trouble here, so I'm trying to see what I should do. Okay, let me see. I think I should probably. So let me try to. Okay, let me try to create space for this turn. Okay, and then wrong, because okay, I obviously for the given area I added too many turns. Okay, so but you get the basic idea. So you want to take this across like this, and this would be your S1 and S2, right? This is fairly symmetric. Okay, you get the basic idea, right? So you have the same number of turns on both the primary and the secondary. You have the same number of metal layers, same width, same spacing, and you have an underpass in the primary, you have an underpass in the secondary, all at symmetric points. Is that clear? Okay, so this is one kind of planar transformer. Okay, let's call it transformer 1. So what do you do? So you see that first thing is you have sideways coupling, right? So what that means is you have if you look at the side view, you have two metal lines going like this and you have some magnetic coupling between those two metal lines. Okay, what happens is the closer they are, the better the coupling. So you might want to reduce the spacing to increase the K. but that will also increase the capacitance. So you have to be worried about that. Okay. In this case, I have, how many turns do I have? 1, 2. I have 2 turns for both the primary and the secondary. Can you see that? So this is 1 turn. This is the second turn. Right? In this case, n equals 2. Okay. And the other thing, of course, you note is that so P1 and P2 are not symmetric. Similarly, S1 and S2 are not symmetric because now you have this on a lower layer or you have larger capacitance at this node, right? They are obviously not symmetric. Even though the primary and the secondary are symmetric, the 2 ports of the primary are not symmetric, which may be okay in certain cases. Okay? Okay. So now the other kind of transformer we'll look at is this. So let's consider a single turn transformer. So let me do a good job of drawing this. Okay. Okay, so obviously okay, this is one case, and let's do it a little bit different. So okay, this is a single turn transformer. Okay, so it's like kind of putting them together, right? Okay, so even in this case there is some slight asymmetry between P1 and P2, but for an n equals 1 case this is actually fairly good. Okay, this is slightly more symmetric than case 1. Here you can have slightly shorter lines here depending on the space. Okay, so n equals 1, and of course it's the same sideways coupling, right? Slightly more symmetric, I guess. Now one thing you should know, since you are relying on sideways coupling between the adjacent metal lines, so the coefficient of coupling K is, there is a certain maximum you can get. Okay, because you are relying on the thickness of the metal. So the kind of coupling you are getting is, so if you look at the side view, so you'll have very good magnetic coupling here, right? But obviously as you go farther away between, current flowing between on the other ends of the inductor, you'll have lower K, right? So there is a certain maximum you can get. It's typically will be 0.8, 0.85, around that much. Now you can also have a vertical transformer. So let's say okay, if let's assume that it's symmetrical, obviously a very bad drawing. Okay, so let's say this is on M6. You can go to M5, and right below that you could draw the secondary. So let's say you are not interested in symmetry, but you are more interested in getting a higher coupling factor, right? Your K is obviously higher because now you have larger coupling between these currents, between these lines, right? So this is this case. Okay, so number of turns is 1 and obviously asymmetric, right? Why is it asymmetric? Because so the primary is on M6 and the secondary is on M5, right? So there's going to be a difference in resistivity, there's going to be a difference in capacitance, there's going to be a difference in losses, there's going to be a difference in everything. Yes. If you are not interested in the symmetry, then this is the way to go. Okay, so I'll give you an example. Let's say, actually, okay. So let's say you're trying to design a differential amplifier. Okay. Okay, so obviously you can't use this kind of thing, even though you want maximum coupling. Okay, because the differential current, when it flows like this, is going to flow like this, right, in the other side. So you want to, the more coupling you get, right, the higher, that means the higher Q you will get from this circuit, from this transformer. But you also want symmetry. You can't use this kind of thing in such a case. However, let's say you have something like this. So you have Vn and it's a differential signal. You want to convert it to single-ended. In this case, you don't care. You want maximum coupling factor, but you don't care about symmetry between primary and secondary. Right? If you can afford the extra Cox, you can perfectly well use this. So which is why I said there is no one thing which is used everywhere, right? There are certain cases where you might want to use a certain kind of transformer. Is that clear? Okay. And what is your transformer equivalent circuit? Of course, you'll have your series resistance on either side, and you have your, right, and you'll have the same thing on here, same thing on this side. You can model it this way. You'd have a certain coupling factor K between this, and you might have some coupling, because you have now adjacent lines, you might have some coupling capacitance between the primary and the secondary, right? So it would be very similar. It will be a similar model. Okay, and the last kind of transformers are, the last kind of inductors we'll look at, multi-level inductors. So let's say you are not interested in the Q of the inductor, but you want to get maximum inductance for a given area, and there are cases where you do want that, okay, where you don't care about the Q because it's already a very either a very broadband circuit, right, or the value of the inductance for a given area where the inductor is already DQ'd so much that you're not using it as a resonant circuit. You may be using it in a different way.
From the biasing supply.
Exactly. If you take power amplifiers, you will often see circuits biased such that you have an inductor from VDD to the transistor. So for example, you could see something like this. And let's say you have some resonant circuit, matching circuit, whatever, and this is your load resistance, right? So you could perfectly well have a case where you're really not interested in the Q of this inductor because you're not using it as a resonant circuit. What you're actually using it is, you're trying to make sure that what property of the inductor do you know about? It doesn't allow current to change suddenly, right? So if you have a very large inductor, it tends to have the same current. So effectively what this is doing is, it is offering a DC bias. Okay, it's biasing the output at this thing, it's biasing the output at VDD, but it is also keeping the current through itself stable. So most of the signal, biasing current flows through this, most of the signal current flows through the output. Yes, that's the reason why. So you have a large inductance here, right? Large enough such that at higher frequencies, it offers a very high impedance. So all the signal current tends to flow into the output. You might have a case like this, where you want to design an inductance of a particular value, but you don't care about the Q that much. Okay? Or another case where you might be interested, there are circuits where you want to do, they are not tuned circuits, but they are actually broadband amplifiers. So you might have a case where your amplifier needs to have this is your normal RC amplifier, right? There are cases where if you use inductors, you can actually get a response which looks something like this. You can get a little bit of peaking. Okay, and this is your original RC bandwidth, 3 dB bandwidth, and this is your new bandwidth. So you can get some bandwidth increase if you use inductors. And there are these kind of cases, you may not worry about the Q because you're not interested in the narrow band sense. Okay, so in those cases, you would use what are called multi-level inductors. So what that means is, so let's say you have wrapped it tightly, okay, on M6. Now what you can do, you can actually go to, okay, first of all, the one thing to note, let's first define a current flow direction. Okay, then what you're going to do, you're going to go to M5. Is that clear? So let's say you go down to M5. Which direction will you wind it in? Same direction, right? Same direction means, do you mean the same direction this way? Or current flow should be in the same direction, right? Because you want additive magnetic fields, you want best. So what you would try to do is probably something like this. Maybe something like this, right? And you try to do it, actually I've done a bad job of this, so let me so you may do something like this, right? And you might be able to use multiple metal layers, okay? And what that means is, if the current flows through like this, it will start flowing through like this. So you try to maximize your overlap area. Okay. So this is the last kind of case we'll look at. Okay. So I think we have exhausted inductors, and I think today's we are right on time. So next class we'll try to go over capacitors. Okay. So we kind of took 2 classes for inductors, but that's okay because you need to know this stuff pretty well. Okay. So we'll look at capacitors and varactors next class. Okay. Now